So we need some way of quantitatively assessing the strength of a transition. What is the intensity of the electronic absorption? And we do that with something called the Beer-Lambert Law. Okay, we can use the Beer-Lambert Law to assess the amount of light transmitted by our sample, and then we can extract from that a constant, which we'll call the molar decadic absorption coefficient, or the extinction coefficient, which characterizes the strength of a transition. And that'll allow us to say more precisely what we mean by a weak transition or a strong transition. So we're going to derive the Beer-Lambert Law. So there's our sample, which has got some light coming in from the left as you look at it. It's hitting our sample, and then we've broken our sample up into lots of thin strips of length delta L. The light that's transmitted has intensity I minus, and the length of that cell is delta L. The amount of light transmitted is expressed as a fraction of the incident intensity. So we do I1 minus I, transmitted intensity minus the incident intensity, and then we divide it by the incident intensity. And we call that delta I over I. Okay, that's the fraction of light transmitted by that thin strip of length delta L. Okay, so in general, what is the intensity or the relative light transmitted going to depend upon? Well, it's going to depend upon whether or not the photon bangs into a molecule as it goes through the sample. Okay, if it doesn't bang into a molecule, then it's not going to be absorbed. Therefore, our delta I over I depends on the concentration of the sample. And also it depends, of course, on delta L, because if the sample is longer, then there's a greater chance that the photon of light will be absorbed, because it has a greater chance of encountering an absorbing molecule. So delta I over I is going to be proportional to concentration, and delta L, the length of that strip of the sample. And so we put a constant of proportionality in there, which I'm calling kappa. And since the way we've defined delta I is always negative, then that's where the negative sign comes from. Okay, so if we want to know the total transmission of our entire sample, then we just have to add together all of those individual elements. And if we make delta L very small, we don't have to sum up all those individual elements. We can replace the summation sign by an integration sign. As delta I becomes very small, we call it di. So we integrate di over I, and we're now calling our intensity, which hits the zeroth strip, I0, and we integrate over all of those strips until we get to the final intensity I. And that gives you the equation ln I over I0 is equal to minus kCl, which we can rewrite, of course, as an exponential function. I is equal to I naught e to the minus kCl. The traditional way to assess logarithm of I over I0 is to use logs to the base 10. So we write that as log to the base 10, and that means on the right-hand side we have to make a correction, dividing by 2.303. And so we include that 2.303 correction into our constant of proportionality, which was k, and that now becomes epsilon. Epsilon is just k divided by 2.303. Epsilon is what we call the molar decadic absorption coefficient, and it's a function of the molecule. So it's independent of the concentration or the length of the sample. It tells us about the propensity of the molecule to absorb light. So if epsilon is a large number, then that's a strong transition. If it's a small number, then it's a weak transition. If it's 0, but you know the energy levels are there, then it's a forbidden transition. So having this epsilon allows us to be quantitative about the strengths of electronic transitions. That whole thing, epsilon Cl, is sometimes referred to as the absorbance. And that equation there, log to the base 10, I over I naught is equal to minus epsilon Cl, is known as the Beer-Lambert law,